final part of the circuit is the power amp. The power amp was designed for a gain of 10 and is shown in the figure. The biasing for the power amp was chosen as listed in the table. The current of 1 amp was selected for the output stage. Using a safety factor of 10, this leads to a Darlington base current of 10 milliamps and a base current of 1 milliamp at the common emitter input. A voltage of approximately 2.8 volts is required at VBE multiplier to compensate for the turn-on voltage for both Darlington paired transistors. A base current of 2 microamps was selected for the VBE multiplier, which is more than enough to avoid the risk of a cutoff condition. The VBE multiplier was the first section of the power amp to be designed. A voltage of 2.8 volts and a current of 200 microamps results in a total resistance of 14K as shown in equation 1. Rearranging the voltage divider equation allows for a resistance ratio of the VBE multiplier to be calculated as shown in equation 2. Equations 3 and 4 show the final calculations for both resistors. The common emitter amplifier was biased similarly to the preamp circuit. However, the values calculated here had to be changed in the physical circuit due to invalid assumptions made during the design process. This table shows the operating points for the common emitter amplifier. These values were again chosen to center the output between VCC and ground as well as to ensure enough current would be supplied to the load. The emitter resistor value was calculated using equation 5. The total of the resistors above the collector was calculated using equation 6. The value was then divided in 2 to obtain the individual resistances. The base resistors were calculated with an assumed IB of 1 milliamp, and the calculations are listed in equations 7 and 8. The gain for the power amp is determined by R11 and R10. R11 was chosen to be 100K, which forces R10 to be 10K, as shown in equation 9. For the final design, R10 was reduced to 9K to help resolve a clipping problem in the power stage.